Today we're talking about rates of change. So here are 4 examples that we're going to go through involving rates of change. For example 1, we have a diagram, figure 1.2a, and there's a function and there are 3 points labeled at x is a, b, and c. We just need to determine whether this function is increasing, decreasing, or neither at each of those points. So let's go ahead and start at x is equal to a. So at x is equal to a, y is, let's look at our graph right here at a, and we read the graph from left to right. So as I read the graph from left to right, y is increasing. We also need to know if it's increasing fast or if it's increasing slow. So when I look at this graph, in the area where A is y is increasing pretty quickly, as opposed to when we look at this area right here, it's increasing less quickly. So I would say here that y is increasing fast or quickly. The next point that we're going to look at is B. So when we look at B, first of all, at B, are we increasing or decreasing? And again, I read it from left to right. So at x equals B, as I read from left to right, my pen is going down, which means that y is decreasing. And again, we have to determine whether it's increasing fast or increasing slow. And when I look at the line that I've drawn quickly, which is called a tangent line, we're going to get more accurate with a ruler in a little bit. That slope, even though it's negative, is less steep than the blue tangent line. So I'm going to go ahead and say this looks like it's decreasing slow. Finally, we're going to look at x is equal to c. And at x is equal to c, again, I'm reading from left to right, but when I look at that point, it's not increasing and it's not decreasing. If I were to draw in a tangent line touches the curve exactly one time, just like a tangent did in geometry with circles. A tangent line touched the circle exactly one time. This tangent touches the curve at x is equal to c. That line is horizontal. It has zero slope. The slope is 0, which means y is neither increasing or decreasing. And I'm going to just write ink or deck because we're lazy mathematicians. So we have labeled our 3 points. And again, we've referenced our tangent lines to determine whether we were increasing or decreasing quickly or slowly. So moving on to example 2, we have a diagram that is terrible, and I apologize, you cannot see the grid lines. On anything else that we give you, you will see grid lines, and it will make it much easier for you to estimate your instantaneous rates of change. So in example 2, we have a figure, and we have the height of a soccer ball above the ground. The height is in feet, and the time is in seconds. So part A, we're going to estimate the instantaneous rate of change of h at time t equals 5. At this point, if you have a ruler or a straight edge, you will want to get it. If you don't, I recommend go ahead, pause the video, and find yourself a ruler, or use your calculator cover if you can. My line is not going to be straight, so I apologize. What we're going to do is we're going to start by drawing a tangent line. So I'm going to go ahead and write that next to part A. I'm going to draw a line tangent to the curve, and we're going to do that at x is equal to 5. So I identify where x is equal to 5, and I'm going to again estimate my tangent line. You're going to use a ruler, and what you're going to do, you're going to lay your ruler down right here, and you're going to scooch it closer, and you're going to scooch it closer until you have approximately a tangent line. And again, you really want to use a straight edge for this. You don't want to eyeball it. Once I have this in place, I'm going to estimate what the slope is. If we had a grid, we would want to look at what we call lattice points. The lattice points would be where I put that black dot, which is actually up here, where the grid lines intersect, so they're your little corners, and that's what you're going to want to use. Now, of course, in this one, we can't estimate it very well because we don't have our grid. We can estimate going up, looks like about 20, and going over about 4 or so. In looking at the grid, I had access to the grid, so I apologize. This slope is actually going to end up being, for part A, it's actually positive or negative, first of all, and this slope is negative slope. It is going down as we read from left to right. So the instantaneous rate of change is approximately negative 56 over 4. I need some units now, and the units on the top are the y value units, and when I'm looking for the y value units, I look at the y-axis. So here's my y value units, and they are in feet. And then my x value units for my slope, which are on the bottom, down here are in seconds. So it's approximately negative 56 over 4 feet per second, which comes out to be negative 14 feet per second. Again, this is an estimate, and you will have a better grid to use this, and you'll see a much better grid in class when we work on this. So whenever we have a question written in a sentence, we want to answer in a sentence. So the instantaneous rate of change of h of t at t is 5 seconds is approximately negative 14 feet per second. Again, those units are going to be extremely important for the entire class, especially in this first unit. So please be sure you give units anytime units are presented in the problem. Part B. Part B says, okay, now go ahead and tell me what the mathematical name of this instantaneous rate is. And that's the calculus right here. We did an instantaneous rate of change. We used slope to estimate that, which is an Algebra 1 idea, but that is the crux of calculus right there, and that is called a derivative. So we have derivatives represent rates of change, more specifically, instantaneous rates of change. Now we need to talk about why is this rate negative? And we need to go back to the real world, or we can talk about the function. So we're going to do both. So first let's talk about the real world. This function represents the soccer ball. So what's happening if my slope is negative? The negative rate of change and that means the soccer ball must be going down. And it's going down or falling, however you want to state that. The other thing that we can talk about is the actual function. And if you look at the graph, we look at our red line, I wrote down here negative next to our red line because our slope was negative. And that's because our function is decreasing at this point if we reference what we did in example 1. So again, the red tangent line shows that the function is decreasing at that time. So we could also say h of t is decreasing at t equals 5 seconds. So moving on to example 3. In this figure, we have a probability for rain based on the number of inches. So in our x-axis, we have the number of inches of rain, and hold on, sorry about that. Our y-axis represents the actual probability, and the probabilities are in percents. So let's look at part A. The probability that it rains 1 inch is P of 1. And if we were to actually calculate P of 1, we would get 24%. So let's go ahead and do that right now using our calculator. So make sure you've got your calculator with you. Pause if you don't. I'm going to go ahead and put the function in y equals. So I push the y1 the y equals button, and in y1 I'm going to put in p of x. So that is 40 times 0.6 raised to the x. And I'm going to go ahead and put that in y1. I need to remember that I put that in y1, so I might want to write that down. y1 is this. Okay. Now in part A it said that P of 1 is 24%. So we're going to quit out of this and go ahead and find P of 1 in the home screen. So second quit. So you're back in your home screen, and I'm going to pull up y of 1 and I'm going to plug in a 1. So I'm going to step you through this in case you don't remember. So to pull up a variable, which is y1, I'm going to press the vars button, which is next to the clear button. And then I'm going to go over to y vars, because I'm looking for a y. So I press the arrow over, and it is a function I'm looking for. So I'm going to go ahead and push enter. And I want y1, that's the function I was looking for. So I'm going to press enter. And right now I need to tell it I want y1 at 1. So I'm going to use my parentheses, just like function notation. And now I'm asking for what is the value of y when x is 1. I hit enter and I get 24, which is exactly what the problem said. It said that p of 1 was 24%. So now we need to answer some more questions. By how much and in what direction does the probability change from x is 1 to 1.1? So it's asking about a change, and it's actually asking by how much does the probability change. So what we're going to actually do is find the average rate of change. First of all, is it going down or is it going up? And when I go from x is 1 to x is 1.1, that probability is going down. To figure out how much, I would need to subtract probability at 1.1 minus the probability at 1. So for this question right here, what I need to do is I need to say, well, if I take p of 1 and I subtract, p of 1.1 and I subtract p of 1, that's going to be how much it's going to change and in which direction it's going down, so it's actually decreasing. So let's go ahead and figure out what that difference is. And again, I'm going to use my calculator. I've already stored p into y1, so I'm going to do the exact same thing I did before. If you know what you're doing, go right ahead. Vars, I'm going to go to y vars. I'm going to choose function. I want y1, so I press enter again, parenthesis, 1.1, and I'm going to subtract. At this point, I could call up y1 of 1 again, but I've already figured out what it is. It's 24, so I'm just going to type in 24 and hit enter. You may do it either way. So that difference is negative 1.1951. When you write down answers for calculus, so I want 4 decimal places and then chop it off. Do not round to that 4th decimal place. Simply give me 4 decimal places and discard the remaining decimals. So now we're moving on to the second part of the question, which is what is the average rate of change? So we've calculated basically y2 minus y1. We need to now divide by x2 minus x1. So to do this part, what I really want to do for the average rate of change is I want to have p of 1.1 minus p of 1, and then I want to divide by the difference in the x's, and the difference in the x's would be 1.1 minus 1. So I've got most of that calculated. I've already calculated the top, which I'm going to leave in my calculator. I'm not going to use the 4 decimal places. When I calculate something else, I'm going to use my calculator's version of that number, the entire decimal value. I am not going to use the 4 decimal places. And I'm going to divide that by 1.1 minus 1, which is 0.1. So go back to my calculator. I already have the negative 1.1951, etc. I just need to hit divide, and I want to divide by 0.1. So that gives me that my average rate of change and it's approximation because it is an average rate of change, negative 11.9519. I do need some units here. So the y value was probability, and we decided probability, the units for probability, again written right here, is in percent. And we were dividing by the x values, and the x values, the units for those were inches. So I have negative 11.9519% per inch is the average rate of change from x is 1 to 1.1. So the next part of the question is, well, great, but why is the rate negative? Now we already talked about the fact that when you look at the graph, it is decreasing. So we have two things we can talk about. We can talk about the fact that P of x is decreasing at x is 1 and x is 1.1. We can also talk about the real world aspect. So when we talk about the real world aspect, the fact that it rains a little bit, the probability of it raining a little bit is quite high. The probability of it raining 1 inch is 24%. The probability of us having 10 inches of rain is very slim. So as far as the real world goes, this is negative. This rate of change is negative because it's less likely that we will have a lot of rain. So the rate is negative because the probability is decreasing as the number of inches increases. Okay, so that was all part A. We're going to move on to part B, which says now let's write an equation for R of x, the average rate of change of P of x from 1 to x. Okay, so the average rate of change from 1 to x. Okay, so those are actually my x values. So for part B, we want the average rate of change from 1 to x. Well, these right here are my x values. So I'm starting at 1 and going to x, which means when we do a slope in our denominator, we're going to have x minus 1. So now I need the y value that corresponds to x. Well, that's going to be p at x is the y value that corresponds to x, and the y value that corresponds to y is p of 1. So this is what our r is going to look like. P of x minus P of 1 all over x minus 1. Another way that we could write that is we could actually fill in P of x, and we can fill in P of 1. We found that earlier, and we were given that in the problem. It's 24 all over x minus 1. Now what we need to do is make a table of values for each 0.01 unit of x from 0.97 to 1.03. So we're going back to our calculator now. So to put this into a place where we can see the table, we need to go to y equals. So when we go to y equals, we're fine leaving our y1 there. I'm going to go ahead and type in our r of x into y2. What I need to remember though when I type it into the calculator is that I need a parenthesis around the entire top of my fraction. And after my division, I need a parenthesis around the entire denominator. So be sure and include those when you key this in. So we're just going to type that in. And double check once you've got it typed in that everything is right. Okay, and hit enter. We've got it saved now. Now we want to pay attention to the table. So I'm still on my calculator and I want to look at my table. I'm going to start at 0.97. So I'm going to go to table setup, which is second window. And my table start is 0.97. And my delta table is my change in the table values. And it told me it wanted me to go for each 0.01 unit. So that's going to be my delta table. Both independent and dependent variables should be on auto. At this point, I can go ahead and look at my table, which is second graph. So I've got my table, and remember, y1 is the probability and y2 is our r. So when I look at my r's, okay, you notice my calculator screen changed. I apologize. I did not realize. I hope you realized when you were doing yours. I did not put my y1 in my y2 in correctly. So I'm going to show you what I did. So in y2, what I was missing is I did not have my minus 24 in my numerator. I missed that. So please make sure to enter that in case you forgot it and you were doing what I was doing. So I apologize. Once you've got your y2 correct, your table should look like this. These values look much more reasonable. So now we need to explain why r of x is undefined at x is equal to 1. So if we look at our calculator, at 1, our y2, which is our r, has an error. So why do we get an error when we do this in the calculator and we look at our function, which I have in blue? What happens when x is equal to 1? What happens to our denominator? Well, when x is 1, we have 0 in the denominator. So it's undefined at x equal 1 because of division by 0. So we can't find the exact value at 1 using this method because every single time we're going to have division by 0. So at this point, we need to do part C. So now the instantaneous rate at x equals 1 is the limit that the average rate approaches as x approaches 1. So we're looking at a limit. So we're trying to estimate the instantaneous rate using the information from part B. We're trying to estimate at 1. So what I really want to look at is I want to look at 0.99 and I want to look at 1.1. So these are the two values that I really want to look at, are that negative 12.29 and that negative 12.23. Now, my calculator is only giving me 2 decimal places. However, if you arrow so your cursor is on a value, it gives you the entire number. And again, we want to use the entire number. We don't want to use a truncated or rounded value. So the average between R of 0.99 and R of 1.01 is what we were going to use to estimate the instantaneous. Rate of change. So all we're going to do is we're going to average these. So we're going to take negative 12.2911, use the entire value. We're going to add that to negative 12. Sorry, negative 12.2285, and again we're going to use the entire value, and we're going to take that and divide it by 2. We're going to do that in the calculator, and again we have R is stored in Y2, so when I quit, I'm going to go ahead and I am going to pull up Y2 at 0.99. I'm going to add that to y2 at 1.01, and I'm going to divide by 2. So a good estimate of the instantaneous rate of change would be approximately negative 12.2598. And again, we will probably need some units here. And our units would be, again, percent for the probability per inch for the x value. So that is example 3. And again, what's key is we need to remember what we did in our calculator, which was y2 of 0.99 plus y2 of 1.01. We took that and we divided that whole thing by 2 to average them. Moving on to example 4. So we have a mass now bouncing up and down from a spring that is hanging from the ceiling. The distance for y is the distance from the ceiling. So as the mass goes down, the y gets larger. As the mass goes up, the y gets smaller. We have a table of values, and time is given in seconds, and y value is given in feet. So part A, how fast is y changing at each time? So what I'm going to do is I have the table down here. The first x value we want to look at is that t value is at 0.3. So because I'm looking at this value, which is sort of in the middle between 0.2 and 0.4, what I'm going to do is I'm going to find the average rate of change between 0.2 and 0.3. Then I'm going to find the average rate of change from 0.3 to 0.4. Once I have those averages, I'm going to average those again. And that's going to give me a pretty good estimate of the instantaneous rate of change, and also a good estimate of the average rate of change because we are forced into this table. So we're going to start by finding this rate of change, and this first rate of change is going to be subtract the y values. Again, we're just doing the slope, and we're dividing by the x values, and I can just work that out on my calculator. And I get 18.5. I'm going to go ahead and do the next one, and that's going to be 7.37 minus 5.84. Difference in the y's divided by difference in the x's. And again, I'm just going to use my calculator to work that out. And in this case, I get 15.3. So to actually estimate the average at 0.3, I'm going to take these two and average them together. So I'm going to take 18.5. I'm going to add that to 15.3. And then I'm going to take that and I'm going to divide by 2. And when I do that, I get, I did not divide by 2. Sorry, I get 16.9. I need to add some units onto that, and that's going to be feet per second. And that rate of change is positive. So we're going to do the same thing at 0.6, and we're going to do the same thing at 0.1. I want you to pause the video here, and I want you to work those out. When you play the video again, the answers will be up on your screen. Go ahead and pause. So the answers are in blue. So at time 0.6, the average rate is negative 9.95 feet per second, and at time 1, the average rate is negative 0.55 feet per second. If you did not get those correct, pause the video here and see if you can figure out your mistake. If you are correct, then go ahead and continue on with the video. Now we need to talk about part B. So in part B, it's asking, at time t is 0.3, is the mass going up or down? Well, let's look at the rate first. We found that rate of change, and that rate of change at 0.3 was the first one we found, which was 16.9 feet per second. And that is a positive rate. If that's a positive rate, that means that y is increasing. And if y is increasing, we need to go back to the diagram. Let's go back to our diagram. In our diagram, if y is getting bigger and bigger and bigger, that means that the mass is moving down towards the ground. So the question is the mass going up or down? And that means the mass is going down. And we are finished with our rate of change examples.